quantum well will give us a good example of what happens to densities of states as we start making structures that are quantum confined. Basically, quantum confined structures allow us to play with the density of states, to engineer it actually. So, just as for the bulk case, we formally impose periodic boundary conditions in the x and y directions to figure out the density of states in k-space, for example. This is going to give us allowed values of the wave vector. In the x direction, values kx spaced by 2 pi over Lx, and in the y direction, ky spaced by 2 pi over Ly. These are going to be the allowed values of the wave vector components in the plane of the quantum well layer. So each kxy state now occupies an area in k-space, kxy space, of 2 pi all squared over the area of the quantum well. That's the size of the layer from side to side, not the thickness, but the area of it. So this is a similar argument that we used for 3 dimensions, but now we're using this argument in 2 dimensions. So this area of the quantum well is a product of the length of the quantum well in one direction times the length of it in the other direction. Not the thickness, as I'm saying, but the lateral dimensions of this layer. And of course, there is one allowed value of kxy for every unit cell in the xy plane of this quantum well. So the arguments to get to this are exactly the same as we used in 3 dimensions. We're just working in 2 dimensions instead. Now, since each of these kxy states occupies this area of 2 pi all squared over the area of the quantum well, the number of states in a small area, d squared kxy of kxy space, is just the inverse of this area taken up by one of the states multiplied by this little element of area. This is the same as we did in 3 dimensions. We're just doing it in 2 dimensions now. Hence, we can usefully define a kxy space density of states per unit real area of the quantum well, and we can call this G2d for 2 dimensions of kxy, and instead of it being 1 over 2 pi all cubed, it's 1 over 2 pi all squared, just because this is an area over 2 pi all squared. In 3 dimensions, it was a volume over 2 pi all cubed. Similarly here, our k-space density of states per unit real area, so dividing out by the area of the quantum well, is given by this expression. So now we can actually properly draw out a diagram, because this is only a 2-dimensional situation, and this 2-dimensional diagram is actually completely correct for this situation. For simplicity, we're taking the quantum well layer to be the same size in both directions, x and y, a length L. So now we're looking at a circle here that corresponds to a specific energy EXY, and another circle that corresponds to an energy EXY plus dEXY. So we're looking at the number of k-states, a number of dots on this diagram that fits in this annular ring between these 2 circles. That number by definition is going to be this quantity. So this quantity is the number of states in k-space, kxy space that is, in this annular ring. And this annular ring has an area that's given by the circumference of this circle times this distance here in k-space, kxy space, between one circle and the other. And that's dkxy. So this is the area of this annular ring. And again, we can write down dkxy in terms of this derivative of dkxy by dexy and multiplied by dexy. And we're going to use that in the same way we used it in 3 dimensions. So, using the assumed parabolic relation then between exy and kxy, we therefore get, multiplying by 2 to include the different spins, exactly analogously to the three-dimensional expression, our factor of 2 from spin, our density of states in k-space, our area of that annular ring, 2 pi kxy times dkxy, but of course we're substituting with this expression for dkxy. Well, just as before, we can work out all of this algebra here. We have our parabolic relation between kxy and e. And working through the same algebra, we get to the following quite simple result. And in this case, you'll note that algebraically, the square roots of energy actually cancel out. And we get the somewhat surprising result that this two-dimensional density of states is actually just a constant. So what is going on here? Here's our picture with our subbands. This relation that we have here then means that the density of states in energy within a given subband is actually a constant independent of the energy within that subband for all energies greater than the bottom of the subband in question. Now, why is this? Well, to understand how many states there are within a small range of energy, we should really take a slice of thickness dE here across these paraboloids. And if you take a slice across the bottom, the slice doesn't end up having a very large radius, but the curve is not very curved down there. So there's quite a lot of k values in there. If you take a slice further up, then there's not so many k values within any given little portion here of energy, because the energy is rising very fast. But we have to remember that we have to take an entire annular ring around this paraboloid, and that annular ring is getting bigger all the time as we go up in energy. And these two effects compensate one another. And if you drew vertical lines from all of these dots here up onto one of these paraboloids and drew slices through the paraboloids, you would indeed find that all the slices had the same number of dots in them as you went up the paraboloid. So therefore, this quantum well density of states is actually a step density of states. And it ends up looking like what we have in this diagram here. So starting at EXY equal to 0, that is starting at the bottom of this particular subband, so there's a finite energy, a 0-point energy, corresponding to E1 here. The density of states of any given band just rises as a step. So the total density of states is the sum of all of those, and we get a series of steps, with each new step starting at the corresponding particle in a box confinement energy, E1, E2, E3, and so on. If we plot this quantum well density of states and plot it per unit volume, so now including the thickness of the quantum well, for a quantum well with infinitely high walls, just as a simple model, we'll find that this actually touches the bulk density of states that we would calculate for something of the same volume. So calculating per unit volume, we would get an e to the half edge, and we see it touches here at the edge of the first step. And actually, since these steps are spaced quadratically, and since this is a square root function, it continues to touch at all of these corners. The bulk density of states would just be a parabola on its side, and the quantum well volume density of states touches that parabola. We can now see that if we started to increase the thickness of the quantum well, the steps would get closer together because the confinement energy would be becoming smaller. But their corners would still touch this parabola. So this height here would be dropping, relatively speaking, but the step would be moving in. The density of states per unit volume would be doing this because the thickness of the quantum well would be getting larger. So this touching of the parabola doesn't depend on what the thickness of the quantum well is. So as the quantum well became very thick, its density of states would actually tend to that of the bulk material, which is a rather reassuring result.